Well, here I am. First, here's a photo of the Legacy Award you have given me, and I greatly thank Michael and all of you for this honor. I congratulate Professor John Ebersol for also winning this award. Now, I'm too frail to fly to Las Vegas in person. I recently turned 91, so we will try this remote version of PowerPoint. And I apologize for the lack of polish, and I apologize for my weakening voice. Incidentally, Marty took this picture. He's a great photographer. Here's my talk, The Birth of the MEG, a brief history. Later I'll add a couple things to it. I wish to give a very brief talk about the birth of the MEG. There is no confusion about different authors. Things are quite simple. There was only me, essentially working alone on the magnetic field of the brain until about 1973 or so. And the purpose of these slides is to give a quick blitz showing how I got here and what I'm all about, really. I was raised in Winnipeg, Canada. That's Winnipeg, folks. Sort of like Boston, isn't it? I attended my first 4 years of university at Manitoba, but I always wanted to be a physicist, and I followed a straight career line, all the way straight as an arrow. Next, University of California, Berkeley, for graduate physics. Talk about culture shock. There's a photo of me doing my doctoral thesis at the Lawrence Radiation Lab. Cyclotron is off on the right. I'm the graduate student in the far left. This is about 1950. The Lawrence Radiation Lab, a lot of shielding, a lot of concrete shielding everywhere. Then after I got my PhD in high energy physics, I did high energy accelerator work at the Argonne National Laboratory. While working at Argonne, I got ideas for measuring weak magnetic fields from the human body. Next is a proposal. Asking the Argonne Laboratory for money to measure the magnetic fields of the human body. I didn't get the money, so I decided to completely switch fields. I left the high-paying job at Argonne to a low-paying job at the University of Illinois, where, however, they gave me money to build my first shielded room for biomagnetism. Here is the campus of the University of Illinois in the middle of Chicago, downtown Chicago. And in the basement of this building, I built the first shielded room for biomagnetism. They gave me the money to do this. There is the first shielded room. It's a homemade job. There's a Sears vacuum cleaner making a vacuum between the doors. 2 layers of polypermalloy and 1 layer of pure aluminum. It really was a homemade job, not a very good shielded room, but allowed me to measure the heart, which was a large repetitive signal. The only detector I had in those days was a coil of wire. And here's what that looked like. That's about 500,000 turns of wire taken apart for illustration purposes only. And I used a similar coil later to measure the brain. I used various forms of ferrite rod to enhance the small expected signal. Notice that this is a room temperature coil. I successfully measured the heart with this, and then went after the brain. The system worked. The heart signal was pretty small. The brain signal was expected to be much smaller. I chose the alpha rhythm of the brain. Here's a signal averaging. The lower trace is one trace without averaging. The upper trace is about 10 minutes of averaging of the alpha rhythm. It took 10 minutes to see one trace of the alpha rhythm. It was horribly noisy. Here's one view of my results. The instantaneous plot of the magnetic field around the head due to a selected group of alpha rhythm. These poor signal to noise results, however, was published in Science in 1968. Here's a picture of the Science cover. This was the first MEG publication. It was actually quite useless, but showed only that a magnetic field actually existed around the head, however difficult to obtain. But the MEG was born. However, I had career problems at the University of Illinois. Luckily, I was offered an interesting deal at MIT, and I moved there in 1969. The first thing I did at MIT was to build a superb shielded room to continue my biomag measurements. That's my MIT room. It was superb, but it needed a low noise detector. The copper coil was too bad a detector, too noisy a detector for the low background of this room. Then along came Jim Zimmermann with the Squid, which he had just invented. It was a perfect combination for biomagnetism. He brought his Squid to my shielded room, and we measured his heart. There it is, the first biomag measurement with a Squid, the human heart, easy to measure because it's a huge repetitive signal. This combination of Squid and good shielded room was the real beginning of biomagnetism. The next day, after measuring Jim's heart, we took a picture. That's a pretty secretary in the background who liked to pose for the picture. That's Ed Edelsack on the left, me in the middle, and Jim Zimmermann, the real star, on the right. I studied the heart on and off for many years, but along the way returned to use a Squid to measure the brain. Here's the arrangement for measuring the brain. The subject sat there, and the Squid is at the head, at his head, almost barely touching his head. One channel, and you could easily see the alpha rhythm of the brain. The first MEG Squid measurement taken in 1971, alpha rhythm On the left, eyes open. In the middle, eyes closed. On the right, eyes open. The first brain measurement of the squid in 1971. Published it in this science paper, and the publication of these results, some people consider this event the real birth of modern MEG, the 1972 science paper. I was soon followed by other physicists, Kattila in Finland, Sam Williamson in New York, etc. Then I was joined by Neil Cohen, a near genius at computer modeling. He became my partner. He passed away. But we were a team. I was the experimenter. He was the theoretician or modeler. And we spent many years on the heart, the brain, the lungs, and measuring DC magnetic fields. Many of you will recall the many papers by Cohen and Cohen in many areas of biomagnetism. Our work, I think, inspired many groups worldwide, including clinical work. We now fast forward 20 years through the MIT lab. During those 20 years, we even had jokes. I'm sorry about that, but here it is. Our one big joke, Neil and me. It's a terrible joke. But we indeed, over those 20 years, carried out many projects. Then, 20 or 25 years later, I closed the MIT lab in about 1995 when I was 65. And in about 1998, 3 years later, Bruce Rosen and Jack Beliveau invited me to join them here at the Martinos Center, where I am now, to help build a superb MEG facility. Here's the building of our facility at Mass General Hospital at the Martinos Center. The foundation is being laid about 1999. This group is gold plating the sheets so they make good contact with each other. And it's a marvelous group, great spirit. And even today, the group is led by Matti Hämäläinen, which means a very happy group indeed. Then about 6 years ago, Shiraz Khan and I, this fellow here, and myself, discovered each other and did some nice projects together. This is still the epilogue. One thing we're very proud of is this paper just published in Human Brain Mapping, using the MEG, actually the DC MEG, to non-invasively measure magnetite in the living brain. I think we're onto something quite useful, so I'll spend a few seconds telling you about this as we close the epilogue. I hope it'll be a new clinical use of the MEG. Here's a picture of the method we propose. First, the idea here is to measure magnetic particles in the brain while the subject is alive. Up to now, measurements of magnetic particles have been made post-mortem, missing the living person. In this method at the left, the subject is magnetized by being slid into an MRI, and his head is magnetized. The magnetite in his head is magnetized. Then he's brought into a shielded room, and the DC, where the DC MEG is measured, and the yellow arrow map shows the DC currents due to magnetite. They're actually the electron currents inside the magnetic material. Then if you do an inverse solution, you come out where the magnetite is. That's the picture on the right, showing a small amount of magnetite in the brain. That's me as a subject. I have about 10 micrograms of magnetite shown there in the bright orange. It is important to note that magnetite presence could be important in the diagnosis of Alzheimer's disease. That is, Alzheimer's disease involves magnetite particles, and perhaps the measurement of the magnetite is important for the diagnosis. And that's about it. Folks, thank you for listening, I hope. But here's a more truthful picture of me. That thing hanging down from my belt is a slide rule, which I used to use in the old days. But I'm still here. Thank you for listening.